Hey,
Hi there, Atticus. How you doing?
I'm doing all right. How about you?
Good.
Good. Ah,
So you said you had a few questions.
yeah, yeah. I guess we're gonna start with question two. Um, I guess first of all, I wasn't under the impression that I thought it was just gonna be section two on the test. And I know there's gonna be stuff from chapter one. So I didn't really go over conditional probability when I was studying. So I've been trying to refresh myself a little bit on that stuff.
Oh, okay.
Um, yeah, it's mostly the conditional probability ones that I'm struggling with. I think there's some independence in there somewhere too. I'm not entirely sure. But question two, the one about the flashlights. Um, it's saying like the probability of type one. Do you have the questions or?
Yep, I'm looking at it. Yep.
Okay.
So here I can show you what I'm looking at right now. Here, so blow it up here and I'll share it. Okay.
So it looks like it's a conditional probability problem where it's like, what's the probability that it's type 3 given that it lasts more than 100 hours?
Yeah.
So you have the different probabilities for each flashlight that they're going to last 100 hours.
Right. Yeah. So what's that first thing saying? So I mean, I don't know, you just need to name that event. Name the event that it lasts more than 100 hours. I don't know.
Yeah, that's what I did.
Call it G or something for
Yeah.
good, or I don't know what you called it.
Yeah, I called it B, but
Okay. So the probability of, okay. So, and what'd you call like the type 1 flashlight?
so the probability that it will be a type 3 flashlight, I called that event A.
Oh, okay. Yeah. So, so what you're given here is the probability of type 1. Okay. So the probability that type 1, okay, yeah. So what is that first what is that first thing saying before the first comma? Probability that a type 1 flashlight will give more than 100 hours of use is 0.7. So that's basically like the probability that it's good, or the probability of B.
Yeah, for a type 1 flashlight.
Huh?
For a type 1 flashlight.
Yeah. So that's the probability of B given that it's type 1. Given that it's type 1. Right?
Oh, okay.
And what's that second thing saying? With the corresponding probabilities for type 2 and type 3.
Type
So
3.
that is if I were to reach in and grab a random type 1 flashlight, so that means that's like my sample space now. I've zoomed into the type 1 flashlights, yes?
Uh-huh. Okay.
And if I reach in and grab a random type 1 flashlight, then the probability that it will last more than 100 hours is 70%. Yeah?
Okay. Yeah.
So you know that the probability of B given type 1 is 0.7. The probability of B given type 2
is 0.4.
is 0.4. And the probability of B given type 3 is 30%. Yeah.
Okay.
And then you know that the probability of being type 1 is 20%. The probability of being type 2 is 30%. And the probability of being
Okay.
3 is 50%.
Is this Bayes' theory?
Yeah. So yeah, Bayes' theorem.
Okay. Oh, I was thinking about it backwards.
Yeah, it's Bayes.
Okay.
So you have all the information you need to use Bayes' theorem to flip the thing around.
Gotcha. Given type 1. Okay. Given type 2. Okay, that makes more sense. All right.
Right. I think that was like the last. It might have been like the very last thing at the end of chapter 1 or something. Yeah.
Yeah, it was like 1.5 or something like that.
Yeah.
Okay. Question 3's got me a little confused too.
Okay.
Oh, 48% of
It's kind of similar in some ways, but
okay. Let's see. Total of 48% of the women and 37% of women took a quit smoking class, remain non-smokers. So it's basically the same idea.
well, yeah. So,
62% of the original class was women.
okay. So how to set this up? All right. So 48% of women who took the quit smoking class remained non-smokers
Mm-hmm.
the 1 year mark. So it looks like our the kind of the sample space is the quit smoking class or whatever.
Okay.
That's what we're selecting, or that's our sample space is the quit smoking class.
Yeah.
Okay. So the probability. So what this is saying is that the probability that that a random class member or the probability that so if I'm just selecting from the women that were in the class,
Mm-hmm.
just selecting from the women. So do you see that? So do you see it's like conditional probability again, because it's like we're zooming in on a part of the sample space. Before, the whole sample space was the whole class, yes?
Mm-hmm.
We're saying only look at the women. Yeah?
Okay.
If I select a random woman, what's the probability that they are still a non-smoker?
That'd be 48%.
Yeah, it'd be 48%.
Okay.
Probability of still non-smoker, given that they're a woman, we're only talking about people that were in the class. Yeah, we're only talking about people that were.
Gotcha.
So the probability that they're still a non-smoker, given that they're a woman.
Given that they're a woman.
Then you zoom in on the other part of the sample space.
Yeah.
The probability that a random student is a non-smoker, given that they are a man,
Mm-hmm.
is 37%.
Gotcha. Okay.
What other information do you have? Well, what about that last sentence right there?
Yeah, you're given the percentage of the total class that were men.
Yeah, so you also know the percentage that were women. We're only assuming there are two genders here.
Yeah, that makes sense.
Yeah. So, so that seems like, it feels to me like you have a similar amount of information that you did in the last problem.
Okay.
But this one, in some sense, is easier. It's not like you're, uh, so now you're trying to find the percentage of people that are still non-smokers. Do you know what I mean? You're trying to find the percentage
Okay.
that are still non-smokers, because those are the ones that are going to attend the reunion or the success party. Yeah.
Yeah. Yep.
So, okay. So the probability that you're still a non-smoker, there's two possibilities. Either you're still a non-smoker and you're a man,
Mm-hmm.
or you're still a non-smoker and you're a woman. That's going to be a sum of two probabilities, yes?
Okay.
It's a probability, and it's the probability of an intersection of two events, which you can compute using the formula for, remember when we were thinking about events in sequence? Probability of A and B is equal
Mm-hmm.
to the probability of A times the probability of B given A, or
Yeah.
we were doing stuff like that. So
Yeah.
you have enough information to compute both of those probabilities.
Okay. All right. I think that makes sense. All righty. Question 5 was giving me some trouble. Because so what I kind of got is, so I just said, X equals the total number of heads that result, right?
Okay.
And so X could either equal 0 or 1 or 2.
Yeah, that's exactly right. Yes.
Okay, so got that part right. So I was trying to find the probability mass function. I don't know, because you're trying to find the moment generating function of X. So my thought process was find the probability mass function.
Yeah,
use
that's
that
right.
to find the expected value function. Use that to find the moment generating
Yeah,
function.
that's right. Yes, 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 yes. So you need the PMF. Yes, yes, yes.
So finding the PMF is where I was stuck.
Oh, okay, okay. Well, what's the probability that that you have 0 heads? What happened? And by the way, the coins are independent.
Yeah.
So the probability of something happening with one and something happening with the other, you can just multiply the probability.
Yep.
So
So that would be 0.4 times 0.3 for 0.
right. Yeah, something like
Zero.
and for one, you have to be a little bit careful because it's like, the one could be head and the other could be tails, or like there's two cases, right?
Mm-hmm.
Getting one heads means that one of the two coins came up heads, and that's like two cases that you have to add together, right?
Okay, you have to add those together.
Well, yeah, because I mean, the first coin being like, if you know that you got one heads,
Mm-hmm.
then that means the first coin was heads and the second wasn't,
Yeah.
or mutually exclusive, right?
Yep.
Or
Mutually exclusive. Okay.
so you have to add those together. But each one of those is going to involve multiplying two things, yes?
Yeah. Yeah.
Okay.
That makes sense.
So that's like one is the most complicated, But 2's easy.
Yeah, 2 is easy.
But you and you should be able to get to check your answer for 1 based on what 0 and 2 are, right? So I cooked this up so that even if you got confused about 1, you could still sort out what 1 is based on what 0 and 2 are. Because what has to be true about those probabilities when you add them together?
Oh, they also equal to 1.
They have to add up to 1, yeah.
Oh, I forgot about that.
Yeah, it's important.
Okay.
So then you should be able to find the moment generating function once you have the PMF. And once you have the moment generating function, it's just easy to find the variance. You just take the derivative, twice and
Yeah.
thing.
So for the PMF, there's no x variable in that function. It's just P of 0 equals a number, P of 1 equals a number, and P of 2 equals a number.
Well, but I mean, so let me see. So the expected value or the moment generating function at t equal to the expected value of e to the t capital X, right? For the variable. But that is, the sum over all little x values, right?
Oh, okay.
E to the t little x
Gotcha.
times the
probability.
Yeah, times the probability of little x, the PMF value of little x. Now,
okay.
So in here, the sum only has how many terms in it? How many?
It would only be 3.
Right. There would be 1 corresponding to x equals 0, 1 corresponding to x equal to 1,
Yeah.
and x equal to 2. So you're gonna have 3 summands, and one of them is going to be really easy because x is 0, and putting 0 in the power of the exponential just
it makes it 1.
makes it 1. And so you're just going to have the probability of 0 left. Then it's like plus, you're going to have an exponential like e to the t times something plus, e to the 2t times something. And that and that thing is easy to take derivatives of. I mean, you could take derivatives as you want.
Yeah. Okay, that makes sense. All right. Yeah, I think that's good. So the last one I was struggling with was problem 10.
Yeah. Okay.
So I set up 2 conditions. So I said O equals the probability that 2 white balls were selected out of all of them. And Q equals the probability that 1 white ball from A was selected.
Okay, say that one more time.
So I said that O equals the probability that 2 white balls were selected, like total. And then Q equals the probability that one of those white balls was from A.
So O is the event that exactly 2 white balls were selected.
Yes.
And A is the event. What is the probability that the ball chosen from urn A was white, given that exactly 2 white balls were selected? So
yes.
So you want the probability of A given O or something?
Yeah. Yep.
Okay.
And so it kind of looks to me like, so the probability that 2 white balls were selected,
Which is the probability of O.
probability of O. So that equal, I'm not sure how to find that.
Well, I mean, you just have to split it up into cases you can handle. So what does that mean? That means because you're taking 1 ball from each urn, right?
Yeah.
So that means either you got a white ball from urn A and urn B, and not
Mhm.
from
Not
urn
urn
C, which you can compute. So that
Yeah.
you got a white ball from urn A,
Hmm.
a white ball from urn B, and you didn't get a white ball from urn C.
Hmm.
Easy to compute because these are independent things, right? So
Oh, so can we multiply them together then?
yeah, right. Those are just independent things because you says 1 ball selected from each urn, right? So there's not even any influence here. Like my selection from the first urn isn't going to impact my selection from the second urn, for instance.
Yeah.
So to compute the probability of O, it's going to be a sum of several mutually exclusive situations. The first of which is take a white from A, take a white from B, and don't take a white from C.
Yeah.
But there's other situations also that you would have to
Yeah.
add. What are
Take a white from A, white from C, and not from B.
Yeah.
Yeah. Okay.
So there's basically going to be like 3 things to add together. And it seems like you should be able to pull it off just based on that, because only some of those sums actually have a white ball being taken from A. You know what I'm saying?
Huh. Okay. Yeah. Oh, okay.
So I mean, I think if you think that through,
Okay.
you'll see it's not supposed to be a very like difficult problem. Once
Okay.
you sort of figure out what's going on with like the probability of 2 white balls, exactly 2 white balls,
Mm-hmm.
you start to say, oh, you just look at that carefully. You say, oh, I can kind of see, I can kind of see I could see how I could get at the probability of getting a white ball from A, for instance. Yeah.
Okay. Gotcha.
Because when you compute the conditional probability, the probability of A given O, that's the probability of A and O divided by the probability of O.
Mm-hmm.
So A
And those.
and O means that I got a white ball. So then all you really do is to compute the probability of A and O. That means that you selected a white ball from A,
Mm-hmm.
and there are 2 white balls. So that means that it couldn't have been one of the 3 situations we just talked about. Namely, you couldn't have taken both those, one white ball from B and 1 white ball from C. That is no longer possible.
Yeah.
Okay, so you should be able to
Okay.
sort that out. Yeah.
Okay. Okay. That sounds good. Thank you very much. Really appreciate that a lot.
Is everything going all right then?
Yeah, it's going pretty good. This is it's been quite the week. It's been quite the week. But sorry.
The lectures make sense?
Yeah, I haven't watched the lectures for today yet, but I was going to do that after I finish this up. guys.
I'm going to go to an exclusively YouTube channel paradigm. I'm finding that some students are having issues with ensemble just not being as I don't know, like it gets bogged down sometimes.
Okay.
That's just a function of it not being as efficient in terms of streaming and streaming quality as YouTube. I mean, YouTube just knows how to do that sort of thing.
Yeah, that makes sense.
So I'll send out a message about that. But other than that,
Okay.
I think I'm just going to keep doing this. It seems to be working for people.
Yeah.
People come and ask questions during office hours and class time. Just a guaranteed time that you could have some face-to-face question and answer,
Yep.
and then just posting the lectures. So I think I'll keep doing it.
Yep. It's been good. Thank you very much.
Oh yeah, no problem. All right, Atticus.
All right. You have a great day.
Yeah, you too. Have a good weekend.
Yep. All right. I'll see you.